All right, welcome back. Today we're going to be going over some game theory because I think this game is really fun and it kind of shows maybe not like a flaw in game theory, but like the science, I guess, behind it, or like the thinking you're going to need, because this isn't necessarily intuitive. So we're going to go over it. And I've already answered it. This is from a little while ago, but thought I'd go over it again because it's fun. You have player 1 and player 2 with either decision A or decision D. And the payoffs kind of work like this. So at this node, I guess I should draw. So at this node, that's not what I want. Oh, there's so many layers. That's fun. Okay. I think this is right. Oh, it's all there. Okay, so player 2 is choosing here to either get a payoff of 5 or 6. Okay, and so player 2 is always going to go down here for the higher payoff, right? Because 6 being larger than 5. Okay. Okay, cool. What else did I do? Undo select layer. Okay. So what's player 1 going to do? Well, if player 1 knows that player 2 is going down to D, and player 1... Oh my god. Player 1 can either choose A, which they know is going to go down to D, or go down to D. And because 5 being larger than 4, player 1 is going to go down to D. And you might be able to sense the pattern here already. So I'm just going to scroll down to my writing here because I don't want to use this pen anymore. It's annoying me. So, like I just explained, player 2, it's always going to be choosing D. Player 1, realizing that 5 is greater than 4, choosing D. And then player 2, realizing that 4 is greater than 3, choosing D. And you're kind of just... There we are. So your sub-game perfect equilibrium is this very measly outcome where player 1 gets a utility of 1 and player 2 gets a utility of 0, which is hilarious. Because remember, we could have had 6, 5. So player 1 gets 6 utility and player 2 gets 5 utility. And that's like, excuse me, that's awesome. But that's not how game theory works. And so I just think this is a fun game. So I just wrote down here, it only makes sense for both players to disagree. So D means to disagree, I guess. That would be more sense. So it's like A to agree, D to disagree. It only makes sense for both players to disagree, even though the payoff is higher the more they agree. This is proven by using backward induction. So this is exactly what we did. We worked backward from the sort of like the final decision there, and we worked our way back all the way in this sort of this dot that's not colored in is the starting point. So then this is what the SPE would look like, where both players are just disagreeing. So because at every decision, both players disagree. And there we have it. This is sort of an interesting... I think this is an interesting game because it kind of showcases... and if you end up learning more about game theory, there's kind of like a way around this, essentially. It's not like... here, I can briefly explain it. So, essentially, this game right here is only getting played one time. Okay? It's only getting played once, which means your incentive essentially is just to get your maximum utility and be as greedy as possible, because you only have one time period to be working with. But essentially, what like solves this is when your time periods go infinite, or like go to like 20 or go to 30 or what have you. And so then there's incentive to not screw over your partner, or your the player that you're playing against. There's more incentive to collaborate because there's more games. Because essentially how the game works, okay, well now I'm getting right into it. So you have like let's call this time period 1, and player 1, player 2, they decide to collaborate or whatever it is, and they both end up with a higher payoff. And then let's say there's like 10 time periods. Well, if player 1 decides, screw you, player 2, I'm going to go for my highest payoff for player 1, then the rest of the time periods, player 2 is going to go for his highest, and then the net is just low for both players. So essentially, these time periods, these time periods make it so that both players want to collaborate for as long as possible. So then that way, they're not triggering the other player, essentially going crazy and screwing you up. So like your payoff for time period 1 could be like 5-5, and the golden shining payoff for you might be 10-0, and you're like, you're getting greedy, and so you go for it, but it's your that thing, the prisoner's dilemma. And then player 2's like, nah, screw you. And then for the rest of the time periods, because now there's no trust, it's like 1-1. And then you were wishing that you hadn't triggered this competition, because clearly 5 is smaller than 1. Wow. Clearly 5 is greater than 1. So, like, if this game if this game had lasted for like 10 time periods or 20 time periods, and like this was what it was, that player 2 and 1 both agree to just agree until they get a payoff of 6-5, and if that's broken, then they get a payoff of 1-0, and player 2, being rational, realizes that's still a win, even though they could be having 6 for like 10-20 time periods, right? Then they would collaborate. So that's how it works. But yeah, no, this is obviously without collaboration. This game is played once, and it's done and over with. It's just kind of an interesting look at it, because you're like, oh my gosh, they could have had their cake and eaten it too.